Vaporization is a process where when we have something that is in the liquid phase, so such as water here, the molecules, specifically at the surface, if they have a high enough kinetic energy, they might be able to break away from the liquid by overcoming those intermolecular attractions. And so the more surface area we have, the faster the molecules are able to evaporate. And so when they have escaped from the liquid, they're in the vapor phase. So vapor is the same thing as gas. It's technically a gas that has the same molecules in the liquid phase right below it. So only a small amount will have enough energy, and this is related to this graph down here. You may remember this from the gas chapter, where as we increase kinetic energy, we shift our overall fraction of molecules. So the total fraction of molecules or percent of molecules under each of these curves is 100%, or a total of 1, right, the area. At a lower temperature, the molecules are moving slower, and so their average kinetic energy is, on average, lower than if we're at a higher temperature, they're going to be moving faster. So if this line represents the amount of energy they need to vaporize and escape the liquid phase, then any molecule at the surface that has higher than that curve will be able to do it. So you can see at cold temperatures, only a smaller amount, versus at hot temperatures, more of them are able to do that. So when we increase the temperature, the rate of evaporation is faster. Once those molecules escape from the liquid, they took their kinetic energy with them. So energy gets lost from the liquid, and the kinetic energy of the liquid is lowered. So unless you continue to add energy into the liquid, the temperature will decrease. Because vaporization is an endothermic process, so it requires energy to be added to the system, where condensation, which is the opposite process, is exothermic, and it releases energy. When molecules escape into the vapor phase, they can then get recaptured if they hit and collide back into the liquid. If they happen to do that, they will again feel those intermolecular forces if their kinetic energy is low enough, and they can condense into droplets of liquid on the surface. So those are opposite processes like I mentioned. So when we have an open container, the vapor, let's say we have an open container, if we go into the vapor phase, our molecule can escape. So our rate of vaporization is going to be greater than the possibility to recondense. The possibility in an open container that your molecules are going to hit back into the liquid is not very likely. Where if I close my container off, I can go into the vapor phase, and then my molecule can bounce around and recondense, and so my rate of condensation is going to be the same and equal to my rate of vaporization, and I will have reached equilibrium. So, and when I have that gas in the vapor phase, it's going to exert a pressure. So the weaker the intermolecular forces are, it means it's easier for those molecules to get into the vapor phase, which means they're going to evaporate faster than something that has higher intermolecular forces. So those easily evaporated liquids are called volatile. So we think like acetone or isopropyl alcohol. If I put those on a surface, after a short time, they will have all evaporated. Liquids that don't evaporate easily are called non-volatile, so you could think gasoline or even like vegetable oil. They are liquids, but they don't evaporate easily. You can leave them out for a long time and they'll still be in the liquid phase. The amount of energy it takes to vaporize something is called the enthalpy of vaporization, or delta H vap. It's always going to be endothermic because it's how much energy you have to put into a liquid, 1 mole of a liquid especially, to evaporate it. You'll find tables of vaporization values. You will not find condensation because it's the same value but just with a negative out front, since it's always exothermic. So you can see here are the formulas. Here are the boiling points. And at the boiling point, what is the energy it takes to vaporize it? and then what energy it takes to vaporize it at 25 degrees Celsius. Note all of these are a little bit higher because if you wanted to evaporate something at 25, you have to heat it up to vaporization and then evaporate it. So it's always going to take a little bit more if you're not at the boiling point. So we're going to reference those in a minute when we practice. So feel free to pause here so you can practice these on your own. For those who are ready, let's start. How much mass of water in grams can be vaporized at its boiling point? So if it's in water, then it'll be at 100 degrees Celsius with 155 kilojoules of heat. So we want to find grams of water, and we have 155 kilojoules. So I can use my delta H VAP, which is in kilojoules per mole, to get out of kilojoules and into moles. So for water, the value is 40.7 kilojoules per mole. Now I'm in moles of water, so I can use the molar mass, 18.02 grams of water per mole. That gives me 68.6 grams of water. In this one, we're going the opposite way, so I want to find how much heat in kilojoules it takes to vaporize 2.58 kilograms of water. So I want to go, just like here we went from grams to moles, I need to get into moles. So I'm going to get we'll have a kilogram is 1,000 grams. And then I'm in water, so I'm going to use 18.02 grams per mole. And then I'm at boiling point, so my delta H VAP I'm going to use is 40.7 kilojoules per mole. And that ends up giving me a total of 5,830 kilojoules, so quite a bit. But we do have a lot more mass, so that makes sense. Okay, so suppose we have 0.48 grams of water at 25 degrees Celsius, and then it condenses on a surface of okay, so let's draw this up. I have an aluminum block, and it's 55 grams of aluminum, and it's at 25 degrees Celsius. So suppose that 0.48 grams of water at 25 degrees Celsius is going to condense on the surface. So the heat released. So I'm going to convert this into moles. And then I'm going to use the delta H vaporization of water at 25, but then make it negative for I'm condensing. So negative 44.0 kilojoules per mole. That gives me negative 1.173 kilojoules. Okay, so that's how much heat gets released from this process. Now we have our aluminum, so when I release that heat, it's going to go into the metal. So I'm going to have my metal. So now I'm changing the temperature of my metal. So I have Q equals Cm delta T. So the energy that got lost is going to go into the metal. So the energy lost from my water is going to be how much energy my aluminum metal gains. So I'm going to make it a positive value, 1.173 kilojoules. And I'm actually going to convert that into joules. So times by 1,000 here. To make it into joules, because our heat capacity is in joules, so that's 0.903 joules per gram degrees Celsius for aluminum, times by my 55 grams. My final temperature I'm going to try to find, and my initial temperature is 25 degrees Celsius. Okay, so once I plug those values in, I'm going to divide those two things over. So I end up getting 23.62. Joules cancel out, grams cancel out, degrees Celsius equals TF minus 25. So I'm going to add 25 to that. And that gives me my final temperature equals 48.6 degrees Celsius. So a little bit trickier, but with just some energy conversions. Okay, so when we have a closed container, like we mentioned earlier, our vaporization is going to initially build up. Once we get enough molecules in the vapor phase, they'll recondense. And so the rate of condensation is going to be equal to the rate of vaporization. So it will look like nothing's happening, but in reality, there's a lot going on the molecular level. And so that's what we have dynamic equilibrium. So we are changing, but at the same amount. So changing a lot for the dynamic part, but we're looking like we're equal. If I adjust the system, so if I change the volume or adjust the temperatures, I'm going to shift in a way to minimize or reduce the effects. So anyway, here initially my rate of evaporization is going to be constant because I'm able to get into the vapor phase. As I create some more vapor, the rate of condensation will increase until eventually they become equal and we're at equilibrium. Once I'm at equilibrium, the pressure that the vapor is giving me is called the vapor pressure. It's substituted with a symbol PVAP. The weaker the IMFs are for the molecules, the more molecules in the vapor phase, so we're going to have a higher vapor pressure and it is more volatile. If I have something in equilibrium, and so here's my equilibrium volume, if I increase the volume, now I have more room, I'm going to increase my rate of vaporization. If I lower the volume, now I'm squishing the molecules together, I'm actually going to force more molecules into the liquid and my rate of condensation is going to go up. But once I've restored equilibrium again, my vapor pressure of all of these systems should be the same once I'm at equilibrium. If I increase the temperature of my system, I'm going to increase the kinetic energy of the molecules. And so I'm going to have more molecules get into the vapor phase, so my vapor pressure will increase as temperature increases. You can see it's an exponential curve, so as I have a small change in temperature, I get a big change in vapor pressure. And when I have weaker IMFs, so something like diethyl ether is weaker, it has its vapor pressure grows a lot at a lot lower temperatures. Now, the boiling point is technically, we think of boiling point as a temperature, and it kind of is, but it's really related to the atmospheric pressure and the vapor pressure. So the normal boiling point is where we are at atmospheric pressure of 1 atmosphere, or 760 torr. It's the temperature at which our vapor pressure equals our atmospheric pressure. So here for diethyl ether, where my vapor pressure curve, the temperature at which my vapor pressure curve hits my atmospheric pressure, that's the boiling point. So for water on sea level, it'll be at 100 degrees Celsius. But here up in Utah, it is lower because we're at a higher altitude, so our vapor pressure is less than that. And so our boiling point will be less than that. Like I said, the normal boiling point is kind of like the standard condition, so that way scientists have something to compare and be consistent with. So that'll be when we're at 1 atmosphere. The lower the pressure or higher elevation, we can see here, the lower the boiling point. So on Mount Everest, we'll have a boiling point of 78 degrees Celsius. So that's the hottest the water will get when it's boiling. And so it's going to take a lot longer to cook things up there because the liquids just literally cannot get hotter because they're boiling at a lower temperature. So when we're when we're increasing the heat, just like we learned in previous chapters, when we change the temperature of a substance, either liquid, solid, or gas, it's going to increase exponentially related to the heat capacity. We use a Q equals Cm delta T equation. When we get to a phase change, though, all of the energy that we add into the substance goes into the phase change. So we're not going to change the temperature of the liquid at that point. All of the energy is going to go into that, so we're going to get the molecules to break those intermolecular forces. Once all of those are broken, now we can add energy into the gas phase here to heat it up again. And then we'll use, when we have temperature change, happening, we're going to use Q equals Cm delta T. When we have a phase change happening, we're going to use Q equals the moles times delta H. And that's what we learned, delta H VAP in this case. For sublimation and deposition, this is a less common phase change, but it's very cool. Basically, sometimes we have some solid molecules that on the surface, they have enough energy to get them to vibrate and break free from the surface and go into the gas phase. And this is called sublimation. When those molecules get recaptured into the solid phase, that is called deposition. I think of like little deposits from gas phase. Deposition. Sorry. And so even some compounds, specifically molecular compounds, they're going to have a vapor pressure even in the solid phase, so it's kind of cool. Another definition for melting is called fusion. We'll use both interchangeably. As we heat a solid, we're going to get those molecules to start to vibrate more. Once they get enough energy to break out of their lattice or their solid structure, they will melt or fuse. The opposite of melting is freezing or crystallization. So again, when we're heating and we're having our temperature change happening, that's going to be Q equals Cm delta T. Keep in mind that the heat capacity or specific heat for the same molecule, but in their different phases will have a different value, which is kind of cool. And once we hit the melting temperature, any heat that we add goes into melting, so the temperature is constant. So just like with vaporization, we have fusion, heat of fusion or enthalpy of fusion. It's always endothermic. And so it's always a positive value. And then fusion and crystallization or freezing are opposite processes. And the energy it takes to sublime, we're going to add up melting and vaporization together. And you might guess which would be a bigger value, melting or vaporizing. Vaporizing, because it takes so much more energy, because you literally have to break intermolecular forces all the way and get those molecules to go into the gas phase, where in fusion you're just getting them to go around. So a full heating curve from solid to gas, it involves 5 segments. Heating up your cold solid to melting, then melting it. Heating up your liquid to boiling, then vaporizing it, and then heating up your gas some more. You don't always have to do this. You can have partial ones. Before we just had heating curves. We didn't do any of the phase changes. So that's possible. So keep track of what temperature you're starting at and ending at and what phase changes happen in that range. And that's how many segments you'll have. In this process, we're going to go from negative 25 degrees Celsius up to positive 25 degrees Celsius. We're going to heat 1 mole of ice, which is equal to 18 grams of ice, or of water in general. So when I go from negative 25 to 0, I'm having a temperature change. So I'm going to use Q equals MC delta T. So I know that my mass is 18 grams. My heat capacity for ice is 2.09 joules per gram degree Celsius. And my temperature change is, I'm going from 0 or negative 25 to 0. So write it like that, degrees Celsius. So here, the energy it takes is 941 joules. And just because I already have a sneak peek of what this is going to look like, our enthalpies are measured in kilojoules, so I'm just going to immediately get into kilojoules. So it'll be 4.941 kilojoules. Once I get to 0, I'm going to melt. So I'm going to use my N times delta H fusion. Delta H fusion for ice is 6.02 kilojoules per mole. So I'll plug into that. Q equals N, 1 mole in this case, times 6.02 kilojoules per mole. And that gives me 6.02 kilojoules. Now to boil, now my heating, I'm in the liquid phase now. I'm gonna heat all the way up to 100. So my delta T will be 100. degrees Celsius. Since I'm doing a temperature change, I'm going to do my Q equals MC delta T. So I have, again, 18 grams times now water, 4.18 joules per gram degrees Celsius, times by 100 minus 0 degrees Celsius, my temperature range. That gives me 7,520 joules. Divide by 1,000 to get into kilojoules, 7.52 kilojoules. Segment 4, I'm going to evaporate or vaporize my gas. So I'm going to use my N times delta H vap. So Q here is 1 mole times vaporization, 40.7 kilojoules per mole. And that gives me 40.7 kilojoules there. And then last one, I'm going to heat my vapor. So I'm going to, since I'm having a temperature change, I'm going to use the Q equals CM delta T. So again, 18 grams. My heat capacity for steam is 2.01 joules per gram degree Celsius. And delta T is 125 minus 100 degrees Celsius. So that'll be 25. Q equaling 904 joules. Divide by 1,000 joules per kilojoule. That gives me 0.904 kilojoules. So what I'm going to do is add those all up. I have 0.941 kilojoules to heat my solid. I have 6.02 kilojoules to melt. 7.52 kilojoules to heat my liquid. 40.7 kilojoules to evaporate. And 0.904 kilojoules to heat my gas. So notice vaporizing takes the most energy. So in total, it took me 56.1 kilojoules to heat up 1 mole of cold ice to hot gas. So when we put all of this together, state changes with temperature and pressure, we get these phase diagrams. So they're going to be happening at various temperature and pressure conditions. So on our y-axis, we have pressure and temperature on the x-axis. We have 3 regions, solid, liquid, and gas. So each of those represents the states. The lines in between are our phase changes. So here we have our melting curve. Here we have our vaporization curve, which we've seen before. And here we have our sublimation curve. And on the line, we are actually in equilibrium between the 2 phases. Some points that we have that are important. Our critical point. This is a point where of high temperature and pressure, where above that we don't have a distinction between liquid and gas phase. We have the triple point, where at that point we're in equilibrium with all 3 states. They exist simultaneously. And for most substances, the freezing point increases as our pressure increases, so we should see something like that. But for water, it's so interesting because of its hydrogen bonding makes it the liquid less dense. So if we look at high pressure at any given temperature, it will tell us who's the most dense substance at that temperature. So at 0, ice or water is more dense than ice, which is what we experience. The critical point is, so the temperature to get to the supercritical fluid is called the critical temperature. The pressure to get to the critical point is critical pressure. Anything above that is we don't have any distinction between gas and liquid. And so when we get that, those conditions where we have pressure going really up, basically we're creating this really dense vapor. And so the density is not such that of a gas, but more of a liquid, but it's so hot that they're not able to interact together. So you have this like interesting fluid that acts like a gas. And at that point, they have properties of both the gas and liquid states. Here are some phase diagrams for different substances. These are what the examples will look like. So at 10 atmospheres, we go for carbon dioxide, from -60, which is about right here, 10 atmospheres, going over to 30 degrees Celsius. We're going to go from solid to liquid, and from liquid to gas. So we're going to undergo 2 phase changes. What state transitions occur if you're at 0.5? So here I am at 0.5 atmospheres, probably right here, -60 up to 30. I'll go from gas to gas, so no transitions. We stay in the gas phase. Okay, water. The last section of this chapter is all about how cool water is, and it is really just so cool. Water is a liquid at room temperature. It's a really small molecule. So other molecules that are similar to it as far as molar mass are gases at room temperature, such as methane and ammonia. But because we have hydrogen bonding between the molecules with water, those add such a strong force that we're able to be in the liquid phase. It's a great solvent because it's polar, so it dissolves ionic and polar molecules such as salt and sugar. It has a really large dipole moment, so it's able to pull apart strong ionic bonds. And even though it can do that, it can also dissolve some nonpolar molecules such as oxygen and CO2 in water, which is really great for, like fish or the ocean animals and plants. It also has a very high heat capacity or specific heat for a molecular substance, which is awesome for, the earth and all of the energy that we get from the sun. It helps to keep our earth fairly consistently temperature and not have huge changes in temperature based on the sunlight. It also expands when it freezes due to hydrogen bonding, and so that makes ice less dense than water, which is pretty cool and really unusual. And then because it has hydrogen bonding, it also has a really high boiling point, which is also great. So it has a really big range of it being in the liquid phase. So water, it's great. We love it, and there are people doing research just on water and all the things that it does because it is really cool. So I think this is a great note to end this chapter on.